So today's topic on digraphs is about tournaments, but it turns out that tournaments are related to ranked choice voting ballots. And I happened to find, because it was released like yesterday, a video from Numberphile on ranked choice voting that uses digraphs the way we're going to do it today as an example. This is on the Discord channel. I will put it up on the web links section of our Canvas page later today. But tournament. What? Okay. A tournament, competition, who competes with whom. There's some sort of formula, single elimination, double elimination tournaments, round robin tournaments. All sorts of options exist. What's a round robin tournament? Everybody plays everybody else once. So let me make a graph out of this. If everybody plays everybody once, then I have a KN for n teams. That'll show me who plays who. But two teams play. Let's make an assumption. They play until there's a winner. No ties. In that case, I can describe the winning behavior as an orientation of Kn. And I will go from U to V as an arc if U defeats V. Okay, somebody remind me again, what's an orientation on a graph? But more than that. That's what defines an arc. You go from one vertex to another. There's a direction on each arc. By default, arcs have directions. Edges don't have directions. That's what defines an arc as opposed to an edge. So what's special about an orientation? Did one. Right. Mm-hmm. Between U and V, there can be only one arc. I can't go from U to V and go from V to U. Well, that makes sense if I'm not allowed to tie, and I'm only going to put an arc if U defeats V. So a complete orientation, every graph, every edge in the undirected graph Kn now gets an arrow. And no other multiple edges are built in. So I can't make any sort of cycle between two edges, between two vertices. Okay. So it turns out that there are only so many ways to do this. I mean, think about it. If I have 3 teams, now let me do it easier. If I have no teams, there's only one option, right? Hey, I win. If there are 1 team, there are 2 teams. My graph looks like that. One of those could be from V to U, the other one could be from U to V, but up to isomorphism, that's it. That's the only tournament with 2 vertices. What about 3? Now here's the point. I'm saying up to isomorphism. So if I draw a picture and it matches the picture you drew if you turn it or if you flip it, those are equivalent. If I relabel my edges, my vertices, and it matches your picture, those are isomorphic. So let me think about this. How could I have victory and defeat going on here? U, V, and W. What could happen? To the right. I should say everybody's got to play everybody, right? Okay, so it's possible that everybody wins 1 game. The other choice, somebody wins 2 games. Now here's the point. Do you want to draw the edge on the bottom? Do you want to go right to left or left to right? Up to isomorphism, it doesn't matter, right? But every edge has to have a direction. So we can decide whether we're going right to left or left to right. It doesn't matter. But here, everybody wins once. Here, somebody wins twice. What do you notice about the rest of it? This person at the top here, this one won twice. Bottom right lost twice. And then this person won 1 and lost 1. Here, I have a clear winner. Here, I don't. If I go to 4 tournaments, a tournament with 4 teams, then there are 4 isomorphic, non-isomorphic graphs. This is page 170. 1 team, 2 teams, 3 teams, 4 teams. By the way, by the time we get to 12 teams, I have 154 billion possible results. If I get to 19 teams, I have 2 times 10 to the 34th. Okay, that's a freaking ridiculously huge number. If I get to 25 teams, I have more possible tournaments than there are atoms in the earth. These numbers get outrageously big, outrageously quickly. I would like to define the property of being transitive for a tournament. But I've seen transitive ideas before. What's our definition of transitive? Not in graph theory terms, just in general. So now let's put that in this form. Instead of relates, use the word defeat. If A beats B and B beats C, then A should beat C. In terms of edges on my graph, by the way, I apologize to all of you in advance. In this section, T is a tournament. In everything else we were doing, T was a tree, right? I ran out of letters again. If UV is in the edge group and VW is in the edge group, then UW should be in the edge group. Okay. Question. I have 2 different graphs that are not isomorphic of order 3. Are either of them transitive? Reese? The one on the right is? Jonah, you were making loops with your hands. Tell me. One of them was, it's the second one. Yes, that's transitive because U beats V, V beats W, so U beats W. And on the left, wait a minute. U beats V, V beats W, but W doesn't beat, oh crap. Aha! Go back to the win counts. Remember, winning is, there's an arc from you to someone else. You win. That's out degree. In this right picture, what are the out degrees? Two, 1, and 0. And on the right, the left picture, they're all 1. Page 170. Here are some tournaments of order 4. Let's look at, somebody pick one. 5, 6, 7, 8. Out degrees. Top, middle, left, right. What are the out degrees of those 4 vertices? T7. Top is 0 in a out degree. What about T5? Hey, wait a second. There's a dot in each of T6 and T7. Look at those 3 vertices, the vertices surrounding the dot. What do you see? A beats B beats C, but C beats A. A beats B beats C beats A. Wait a minute, what does that tell me about those 2 triangles? About those 2 graphs of order 4, they fail to be transitive. This one, on the other hand, T5. Every possible triangle, of which there are only 4, satisfies our transitivity idea. The outside triangle, the triangle in the upper left, the triangle in the upper right, the triangle in the bottom center. They're all transitive. Ooh. By the way, same little triangle in T8, right? So out of all 4 of these, only this one is transitive. If I have a transitive tournament, then there's a vertex of degree 0, degree 1, out degree only. 0, 1, 2, all the way up to n minus 1. If I've got order n and the tournament is transitive, somebody beat everybody else. Somebody lost to everybody else. And every other possible arrangement of wins and losses, every possible record exists. 0 and n minus 1 wins. Holy crap. Why? Well, it turns out that it is exactly that little triangle that was our problem. exactly that non-transitive triangle that is our issue. And that little non-transitive cycle is exactly that, a directed cycle. When I read the proof in the book, it made my head hurt. I mean, I ground my teeth for a good 15 minutes trying to understand it. It's proof by contradiction. And I'm not sure it's completely outrageous, but I didn't like it. And so rather than me telling you, hey, go read the proof in the book, it's nice and easy, it ain't. I'm going to write a different proof. That's why I actually wrote theorem, because I want to prove this one, because I want to prove it in a way that's different than the book. And it's this direction that's different. Assume our T is transitive and that it contains a cycle. I am about to perform an induction argument to get to a contradiction. When I tell you I thought this was the easy version, that should tell you what I think of the proof that's in the book. Okay. I have a cycle. I'm going to induct on the length of the cycle. If K equals 3, well, then this says V1, V2 is an edge in my tournament, and V2, V3 is an edge in my tournament, and V3, V1 is an edge in my tournament. And that's a contradiction, isn't it? Because by the principle of transitivity, if V1, V2 is in there and V2, V3 is in there, V1, V3 should be in there. And I see V3, V1. And I can't have both because it's an orientation. Proceed inductively. If V1, V2 is in the edges of T, and V2, V3 is in the edges of T, that means that V1, V3 must be in the edges of T for my graph to be transitive. Then V1, V3 is in my edges, and V3, V4 is in my edges. Yes? Therefore, V1, V4 is in my edges. Continue, and you see that V1, VK is in my edges. Why is that a contradiction? Hint, go back and look at the cycle. You can't have both VK V1 and V1 VK at the same time. Now that means if, because I used transitivity in all of this, if it's transitive, I can't have a cycle. That's part one. Part two is 2 lines. Suppose my graph is acyclic. And pick 3 vertices. What do you know must be true about the arcs between those 3 vertices? Yes, absolutely, because we are taking Kn and putting directions on all of it, so there has to be an arc between U and V, there has to be an arc between V and W, there has to be an arc between U and W. So let's pick 2 of those and decide what directions they are. We'll label our vertices appropriately. So I say, oh, look, there's an arc this way, call that U and V. There's an arc this way, call that V and W. What do you now know must be true about the edge connecting U and W? It can't be W to U, because that would make a cycle. Which means it's got to be UW. Isn't that the definition of transitive? Yay! All right, I lied. It was 3 lines. I write smaller in my notes. It's therefore 2 lines in my notes. Transitive tournaments have lots of really nice properties. Every vertex has a different out degree. They contain no cycles. Wait a minute. Somewhere in that transitive tournament, there's a vertex whose out degree is n-1. We beat everybody. The distance, the directed distance from that vertex to anywhere in the graph is 1. So there is a unique vertex of out degree n minus 1. If that's v, then the directed distance from v to anywhere is 1. But that's only true about the vertex of largest degree, largest out degree. As a matter of fact, all of the vertices have the same total degree. Out degree plus in degree must be n minus 1 because we're working on kn. Got to be same degree total, but the out degrees are all different. The vertex of maximal degree is only 1 unit away from anything. What if it's not transitive? Go back and look at page 170 or at our two triangles. Tournaments of size 3 or size 4 that I already drew. Well, it turns out that that vertex with largest out degree might not be n minus 1 this time. But I can still put an upper bound on the distance. It turns out that if you take the vertex of maximal out degree, it's never more than 2 steps away to any other vertex. So really, I need to think of the vertices 2 different ways. I don't know how many vertices there are, but this is the most out I can go, right? From U, that's the highest out degree. So I'll take the out degree, call it K, and I'll look at everything V1 to VK that comes out from U. There could be a bunch of other things that go into U, but there are only K things that go out, and that's the most out I can do. Well, it could be that one of these is adjacent to one of these. So maybe V2 is adjacent to W whatever, because these are the ones that are not out from U. Well, then to get there, I go to V and I go to W, right? No problem. What if I can't? If I can't get from any of these V's to here, I have a problem. Why? There must be an edge between every one of these V's and this W. If I cannot get from V1 or V2 or one of these to here, why is that a problem? That's only if it's transitive. And I said this is not necessarily a transitive tournament. This is any kind of tournament. If I can't get from W2 to from V2 to WL. Then there's an edge from here to here, and it goes that way. Wait a minute. If I can't get to any of these, then there are K edges coming out of here that hit all of those. But there's also an edge out of here that hits U. What's that make the out degree of this vertex? And K is the largest out degree we could have, isn't it? I just found a contradiction. So at least one of these vertices has to have an edge that goes to this one, no matter what these vertices are, which means that the distance to any of those W's is 2. I go to the corresponding V, and then I go down. There's no way not to be able to do that, or you'd have a vertex whose out degree was higher. And this is the biggest out degree I can get. Contradiction. That picture was, to me, the key insight of that proof. Rather than write out the entire proof, I said, hey, let's see if we can figure this from the picture. What does this mean in an actual tournament situation? This distance being less than or equal to 2. What does that mean? In a transitive tournament, we had a clear winner. Somebody beat everybody else. But in a non-transitive tournament, that distance being 2 means that either team U beat team V directly, or they beat someone else who also beat them. Even though they lost directly, they beat someone else who beat them. This is the any given Sunday idea. On any given Sunday, any team can beat any other team, right? I don't know that, hey, the Steelers beat the Jaguars beat the Browns, we're going to beat the Browns. I hope it works that way, but it doesn't. Much less go to baseball where there are a gazillion games, right? 168 of them will be playing forever. Tournament with 168 games. Oh my God, just imagine the diagram. By the way, at the National American Association of Statistician conferences, there's an entire day devoted just to baseball. The most statistically analyzed game ever in the world is baseball. And that surprises me because I would have thought soccer would have beat it out in a heartbeat because there are a lot more countries that deal with soccer than baseball. But baseball geeks are very special geeks. There are a lot more things you can keep track of in a baseball game. Okay. Go back to the pictures on page 170. It's a digraph, right? Digraphs may or may not have cycles and circuits. What we called these things, a Hamiltonian cycle went all the way around, right? And an Eulerian circuit went over every edge. If I'm in a digraph, I probably won't be able to go over every edge. We said that maybe if the out degree meets the in degree, but that would make my tournament not transitive. Because that would mean that vertices with the same out degree exist. But I could visit every vertex, maybe. Look at the ones of order 4. Let me start with that. Maybe not in a cycle. What about a path? What would be a Hamiltonian path? How would our phrasing change? We know what a Hamiltonian cycle is. What would be a Hamiltonian path? Need a definition. Okay. Pick a graph. Seriously, somebody pick a graph. Regardless of whether it's transitive or not, I may not be able to find a cycle. Matter of fact, if it's transitive, I can't have any cycles, but I can have a path. Okay. But now we're talking about a path rather than a cycle. So I have a Hamiltonian path in a digraph. Clearly, I have a Hamiltonian cycle as well. Now, if I have a Hamiltonian cycle, then I'll call it a Hamiltonian graph. Well, now I'll do the same thing for digraphs. If I have a Hamiltonian cycle, I have a Hamiltonian digraph. Jonah, not only can I do it for all of those triangles on 4 vertices, I can do it every time. Every tournament needs a Hamiltonian path, whether it's transitive or not. But wait a minute, that means once I find that path, I start at this vertex and I go through every team, right? Because that's what every vertex is. Each vertex is a team. But then I have team 1 beats team 2, team 2 beats team 3, team 3 beats team 4, team 4 beats team 5, all the way to the very end, don't I? I have a chain of victories in this path. Now, this isn't necessarily a true ordering because there may be more than one Hamiltonian path in my tournament. If T is transitive, then I won't have any cycles, but I will still have a path. But if T is not transitive, I could have a cycle. If I have a cycle, I have a Hamiltonian cycle, then I can get there and get back. What did we call that sort of an orientation? Ha! This may or may not give me a strong behavior. If I am looking at a strong tournament, then every single trio must be an oriented triangle. So not only do I have a graph where I have a cycle, I actually have all cycles. So if I've got a strong tournament, and it's all cycles, that means there needs to be a biggest cycle. That biggest cycle will be Hamiltonian. So being strong in a digraph is a criteria for being Hamiltonian. We couldn't do this for regular graphs. There was no condition that guaranteed me a Hamiltonian cycle. But I can do it for digraphs. There is a direct condition. That's impressive as hell. Problem. What does this have to do with voting? Cycles. So one of the problems we have, simplest problem in voting, is when we have more than two candidates. Right now, how many people are running for president? It depends on what state you're in, because different people qualify for ballots in different states differently. I believe in the state of Pennsylvania, there are at least 4 people running. You've got Jill Stein running for the Green Party, I think. And there's another candidate further right of Trump. So there are 4 candidates for president here. You only get to vote for one. What if you got to rank your choices? Vote by preference. A over B, B over C, C over D, or whatever preference you have. I don't put it at the top. You've got to write all 4 names. Your ranking is a tournament. Does your tournament have a clear winner? Only if it's transitive. The Marquis de Condorcet in the 1700s proved that voting paradoxes exist by looking at ranked choices. Later, a gentleman by the name of Ken Arrow would win the Nobel Prize for showing that there are no voting systems without some sort of voting paradox. So as much as we get to go vote next week, it still ain't a perfect system. Watch the video I linked. I'll see you all on Friday.